Everyone, how are we today? Okay, good. Right. Again, as usual, let's recap what we have learned last week. Last week we talked about the single component phase equilibrium and the Gibbs phase rule, right? Okay. So this is a summary of the things we learned. Basically, first of all, we learned phase diagrams for a single component. So this is a phase diagram, right? So we have temperature in the x-axis and pressure in the y-axis. So you will have solid, liquid, and gas phase. Of course, you will have a supercritical condition, right? Above the supercritical temperature and the supercritical pressure. So this is the phase diagrams you need to know related to the solid, liquid, and gas. And of course, you know the line represent the line represent two phases. So if a temperature and the pressure located on the line here, and for example, this is the solid and liquid phases, right? And if the points stay in the line here, that will be liquid and gas phases. Of course, this is what we call triple point. Triple point is the one the substance has solid and liquid and gas, three phases at the same place at the same time. And after that, we remove the solid phase and we start to learn liquid and gas system. So this is a liquid and gas system. So liquid and gas system really play with the temperature and the pressure. So we want to know the composition in the liquid phase and also composition in the gas phase. So I use X and Y to represent the fraction of the A species and the fraction in the Y species. Fraction of the YA to represent the fraction in the gas phases. The important thing in the gas liquid system is what we want to know, the vapor pressure. Okay? And another way, what we call vapor pressure is called volatility. If you have a high pressure, that means the volatility will be high. If you have low volatility, that means the vapor pressure will be low. Okay? And then once we know the relationship between the volatility and the vapor pressure, and after that we start to learn how do we estimate the vapor pressure for a single component. And because in the section, in the chapter, in the section 6.3, we are going to learn multi-components. Okay? But anyway, for a single component, first of all, we learn is called Krypton equation. Right, it seems a little bit hard, right? So let me call it TA. Okay, so the first equation we learned is called Krypton equation. The Krypton equation is a relationship between pressure, temperature, volume, and what is this? Anybody want to tell me what is this? 0.5 point. What is this? H. What is this? In Chinese? Yes? 潜热, right? Thank you. Thank you. It's called latent heat. Latent heat is the one when you change the phases, the temperature then goes up. The temperature, the energy is to be used for the transfer of the phases. It can be from liquid to solid. It can be from solid to liquid. It can be from liquid to solid. Liquid to gas. And this one, delta HV, V stands for vapor. So here, latent heat in this equation is specifically related to the energies required to transfer the substance from the liquid phase to the gas phase. So this is called what we call latent heat. Okay, this is what we call Krypton equation. And after that, we learn Clausius Krypton equation. The Clausius Krypton equation is that there's another parameter here is B. We use B is a constant. B is a constant. Okay. So according to these two equations, we will realize how to find out the vapor pressure. Okay. And after that, we learn Antoine equation. Antoine equation is rather simple compared to Krypton equation and Clausius Krypton equation because there's no latent heat, term of latent heat here. So there's only the vapor pressure is only related to the temperature. And A, B, C are the three parameters, which depends on the different substance. It can be water, will have A, B, C, or alcohol will have A, B, C parameters. These three parameters will be different from varying by the different substance. Okay, and later on we learn how to get the vapor pressure from Koch's chart. This is very, very easy because instead of using equation to find out vapor pressure, you can use chart, which we call Koch's chart. We use Koch's chart to get the vapor pressure. Right? This is temperature and this is pressure. And the line here is represent what? It's a very different substance. And this is a log-log plot. Of course, you know that. Right, so in a section 6.2, we start to learn Gibbs phase rule. What's Gibbs phase rule? For example, if we have two substances in this system, and we need to know what's the fraction of each substance, or each component. Okay? So dF represents degree of freedom for the gas. Gibbs phase rule will be 2 plus C minus pi. Does anybody want to tell me what C represent? What is C? Anybody 0.5? Raise your hand if you don't have very nice midterm exam score. What's C? Anybody want to tell me what is C? No? No? 0.5. This is so very easy. What is pi? What is this? What is this for? What is this represent? What is this? Pi. Nobody? 0.5. No? 1 point. No? 1.5? No? Okay, forget about this. Okay. All right. C is component, right? How many species in this system? Pi is the phases. How many phases in this system? So if you have dF is 2 plus C minus pi, that means what? That means it depends on the degree of freedom analysis for the Gibbs phase rule. If dF is 0, that means the system is fixed. If dF is 2, that means what? 2 pieces of information required in order to complete this system. What is this system? Fraction in liquid phase, fraction in gas phase, vapor pressure, and pressure, total pressure, and the temperature in this system. So what you need to know is the information information sufficient to repeat the system or to duplicate this system. Right? Okay. So this is what we have learned in the last week. So today we are going to move to a more excited topic. This is interesting. In this section, 6.3 liquid gas liquid system has only one condensable component. This is a system is getting complicated. I want you to use your imagination to work with me on this topic. So what is the gas liquid system? Of course, you know gas liquid system is in this closed system. You have liquid and you have gas. And 6.3 is that there are many types of gases, like water, water vapor, argon, right? Nitrogen, oxygen, helium, for example. You might have 3 or 5 types of the substance. But however, there's only one condensable component. What does that mean? One condensable. There's only one can become liquid. Okay, in a condition we set. Okay, you might say, well, Professor, nitrogen can become liquid. But if you want to make nitrogen become liquid, we need to make it under very heavy pressure, right? So we liquefy nitrogen gas at a very high pressure. But this is not a case we are going to talk about in this section. Because that's a very high pressure. We don't talk about very high pressure and temperature, extreme temperature in this case. Okay? So what I want to tell you is that, for example, if I have water here, if I remove water, I make it become alcohol, acetone. So this alcohol can be condensed, or acetone can be condensed. Not only alcohol, acetone. So it's only one condensable component. So we might play with the different temperature and pressure to make this system, to make this happen, right? We can, for example, if you want to make the water condense, do you want to increase the temperature or you want to decrease the temperature? You want to make this water condense, the temperature should be what? Should be decreased, right? You should decrease the temperature to make water condense. Right? If the temperature is high, the H2O tend to become vapor. Right? How about the pressure? If you want to make the H2O condensed, you want to use high pressure or low pressure? High pressure, right? High pressure. Okay, so temperature will be decreased, pressure will be increased in order to condense H2O first. Okay, in this case, H2O will be condensed first. Okay, so in this case, we'll have different fractions. So once you play different temperature and pressure, and you will have different fractions, right? However, because water is the only one can be condensed, so the fraction, this is called fraction, right? Molar fraction. The fraction will be always equal to 1 in this case. Right, so one condensable component, instead of using air, nitrogen, oxygen, H2O, argon, we use A, B, C instead. Okay, to represent each component or each substance. Okay, so only one can be condensed. That means A can be condensed, not B, C, D, E, for example. So you will have different fraction of A, B, YA, YB, YC. This is molar fraction, and A will be condensed. So the fraction, molar fraction in liquid phase, XA will be always equal to 1. There's no YB, there's no XB, XC, XD. No. That will be equal to 0. Okay. So systems containing several components, of which only one is capable of existing as a liquid at the process conditions, are commonly in industrial processes. Okay, this is one of the this is the common industrial processes. Okay, so make the gas or vapor become liquid phase. Okay, we have special term for this. We call condensation. You might say, well, Professor, this should be Z. Well, this is English writing. Okay, not American writing. Condensation, or we call dehumidification. Dehumidification especially refer to what? Refer to H2O only. We call dehumidification. Others, like condensation, can refer to, like what I say, H2O, alcohol, or acetone, for example. Okay? But especially for water, we use dehumidification. Okay. How about liquid to gas phase? Well, if air can be condensed, of course, air can be vaporized too, right? So this is what we learn. We know is evaporation or drying. Drying. Okay, this is what we call unit operation. unit operation. Right, so here I use an example for you to have a better understanding. Is the components in the system can be water, nitrogen, oxygen, and carbon dioxide. For example, there are 4 types of substance. Okay. However, there's only one can be condensed. Right. Let's have a scenario, which is air and H2O as an example. Air and H2O as an example. Okay. So let's think of if I have a dry air at a time which is this time equal to 0. So in the very beginning, this is the system which has a dry air. There's no water inside, only air. So at temperature is 75 Celsius, and the pressure is 1 atm, which is 760 millimeter mercury. Right? Okay, this is the dry air. And then at that time, the vapor pressure, remember we always talk about vapor pressure. The vapor pressure of water will be equal to 0. Of course, there's no water. Okay? Right, and then at this time, you pour the water in to this system. Now what happens? You pour the water into this system and you close it. You make it as a closed system. And you have water, of course. And at this time, because the temperature is 75 Celsius and the pressure is 1 atm, so the water will be what? If the temperature here is low, so this water will be vaporized. We call evaporation, right? And of course, the time will be, the time will be increased, right? It can be to 1 minute, 2 minutes, for example. So the pressure, the vapor pressure of water over H2O in a gas phase will be more than 0, because this is 0, there's no water. And then the vapor pressure of water will be more than 0, will be greater than 1. That means what? The pressure represents the amount of the H2O in the gas phase, right? Okay, this is in the gas phase. So the concentration of the H2O in the gas phase increase. So that's why the vapor pressure increase. Okay, this time equal to 0, greater than 0. Okay, and then eventually, now the gas, the H2O reached to the equilibrium, which is what we call the vapor pressure was saturated. So there is no, the H2O cannot be increased anymore. Saturated. So in this case, what we call is no change occurs in the amount of or composition of either phases. So the water in liquid phase is no more decreased, and the vapor in the gas phase is no more increased. So the gas phase is then said to be saturated with water. Okay, so this is what T equal to T saturated. And this is what we call saturated vapor in this case. So it depends on different temperature and pressure in this system. Right? It depends on different temperature and pressure in this system. We will have what? We will have different vapor pressure. Right? We will have different vapor pressure. And if we have different vapor pressure, I might ask you, what is the molar fraction of the water in this system? So I mark these 4 parameters as in red color. That means what? When you play with temperature and pressure, you will get different vapor pressure and you will get different molar fraction of the water in the gas phase. Okay? Right, that's why we need to play, we need to use give phase rule. So, and do you remember what's the relationship with the molar fraction with the vapor pressure? Where can you get this vapor pressure? So vapor pressure will equal to what? The molar fraction times P. P is what? P is this pressure, the total pressure here. So what do we use this? What is this called? Dalton's law, right? We learned this in the chapter 5. Remember? Dalton's law, we learned this in chapter 5. The partial pressure of the H2O equal to the molar fraction of the H2O in the gas phase times what? The total pressure. This is what we call Dalton's law. So you know the relationship between the molar fraction and the partial pressure of the H2O through Dalton's law. Okay? Right. So now what we need to know, what we need to learn is what's the temperature relationship between temperature, pressure, molar fraction of the water, and also partial pressure of the water in the gas phase. Okay, so let's think of DOF variables. So as I just told you, you have temperature, pressure, and molar fraction. There are three. You might say, well, Professor, where is the vapor pressure? Because Dalton's law. You don't need to worry about partial pressure of the H2O because you can use Dalton's law once you get the answer of the molar fraction in the liquid phase. Right, so there are only three variables. Okay? And what's the DOF? How many information I gave you so you can get these three? Should I give you these three? Of course, if I give you these three information, you can complete this system. But if I give you one, can you solve the problem of the another two? Or how many pieces of information required in order to complete this system? 1, 2, or 3? So let's use DOF. So 2 plus C. C is what? I just told you, this is the components, right, in the system. How many components in this system? 1, 2, or 3? 2. You must say, well, Professor, it's not, it's 3. Because air is oxygen and nitrogen, right? Why can we write 3 here? Why? Because oxygen and nitrogen, there is only one independent variables. It's not two independent variables because the ratio of the oxygen and nitrogen is a constant. So they only have one independent variables, not two. If you have two independent variables, that means you have to plus 3 here. But it's 2. Okay, so this is only one independent variables. If I say that, well, in this condition there's oxygen and helium and water, then you should write 3 here. But this is air. Okay? So what's how many phases in this system? 2, right? 2. Right? Gas and liquid. Gas and liquid. So as a result, DOF will be equal to 2. That means what? That means if I provide two pieces of information in this system, for example, I give you temperature and pressure, you can find out the molar fraction. Or if I give you a total pressure and the molar fraction, you can find out the temperature. Okay, if I give you the molar fraction of water in the gas phase and temperature, you can find out pressure. So I provide two pieces of information, and you can get the third one, the third variables. Okay. So only 2 out of 3 intensive variables TP, and the molar fraction H2O can be specified. Some relationship must exist that equally determine the value of the third variables once the first 2 has been specified. So the important pieces of information here is that there's some relationship between these 3. Right? Some relationship between these 3 so that you can find out if you have another 2, you can get number 3. Right? So what is this? What is this? So, but before we talk about this, how to get the partial pressure? Once you have temperature and pressure, you get this, right? Because some relationship. Here is we call Law's law. Law's law. I'm going to introduce this equation to you very soon, okay? So Law's law can tell you the relationship between pressure, temperature, and the molar fraction. And if I give you 2, you get another 3. Can you find out this? Yes, no problem, because this is Dalton's law, right? Dalton's law. Right, so Law's law is the information, the relationship between temperature, pressure, and molar fraction. So Law's law for a single condensable species is that, so we use Law's law a lot. So Law's law is the law describes the behavior of the gas-liquid systems over a wide range of the condition, provides the desired relationship. What's the relationship? Temperature, pressure, and the molar fraction. So what is this? So ladies and gentlemen, I want you to remember this well, because in your final exam, you are going to use this. I'm not going to provide this equation to you. You need to remember this very well. Otherwise, I'll see you next year. Okay? Okay, PI. I is a kind of partial pressure. Partial pressure here, right? Okay, equal to YI. YI is the molar fraction. Okay? Molar fraction of the I species. P is the capital P is the system pressure. System pressure here. System pressure here. Okay, this is not a general Law's law. This is a specific Law's law for one condensable species. The real Law's law is like this: Yi times capital P equal to Xi times the Pi star function of T. Pi star function of T is that the vapor pressure at temperature, certain temperature, times Xi. However, you might say, wow, Professor, you need to remember this equation. This is general Law's law. However, this equation will change to become this one is because Xi is what? Xi is the molar fraction in the liquid phase. And molar fraction in liquid phase for H2O will be equal to 1 because this is one condensable species. So it's always 1. Only one condensable here. So Xi is equal to 1. That means what? If you remove this term here, it's 1, right? You don't remove, it's 1 here. So this Yi P, capital P equal to what? Pi star function of T. So you understand Pi star is a vapor pressure, the pure component vapor pressure at the system temperature T. So if you change the temperature T, the vapor pressure will be changed. Okay? Right, so remember this equation, we are going to work on this equation. I give a very simple case is that in this system, if I give you temperature and pressure, can you find Y molar fraction here? How to obtain Y molar fraction H2O if the pressure and the temperature are known? I give you temperature and pressure, and if I give a temperature and pressure, you want to know the molar fraction. That means what? You need to apply this Law's law, right? So I give you the pressure here, I give you the temperature here. So if I give you the temperature here, and then you can find what? You can find the pure component vapor pressure at the system temperature T. So how can you get this? You learned this in the section 6.1, right? Clauser's equation. Clauser's equation, right? Clauser's equation. Koch chart. Anton equation, you can get this. If you have a temperature, you can get this. Right? So I give you the temperature, you can find out the saturated vapor pressure. And I also provide you the pressure here, so you can get Yi. So how to obtain H2O if the pressure and temperature are known? Law's law, right? Law's law. This is Law's law. Okay? And then, so temperature, and if you have a temperature, you can get this. Vapor pressure. Okay? And if you have a vapor pressure, you have a total pressure, you can get molar fraction. Gauss law. Okay, so by the Gauss law, and you have molar fraction, and you get the total pressure and the molar fraction in the gas phase, you can get partial pressure of the H2O in this system, right? Okay. So there are 4 parameters you need to know. Here is temperature, pressure, molar fraction, and partial pressure in gas phase. Okay. Right. So now let's have an exercise with an example. 6.3-1. Composition of a saturated gas vapor system. Saturated means what? This system has reached equilibrium. That means the composition never changed with the time. Okay, so it reached the equilibrium. And this is saturated vapor, never changed. Okay, so if I ask you, is the air, liquid water at 75 and 760 millimeter mercury reached at equilibrium? Calculate the molar composition of the gas phase. So I want you to find out, if I give you the temperature and pressure, I want you to find out the composition in the gas phase. Composition means what? The molar fraction of the water and molar fraction of the air in the gas phase. Of course, the molar fraction in the liquid will be, water will be 1, right? Okay, so there's no point, there's no way to measure the molar fraction in the liquid phase. Right, so 75 Celsius and 1 atm. So you have air and water, right? And in the liquid phase, it is H2O. So H2O will be equal to 1. And what you don't know is the molar fraction of H2O in gas phase. And once because this Y air plus Y H2O equal to 1. Molar fraction of air plus the molar fraction of H2O is equal to 1. So of course, if I mark this in red color, you don't need to mark this as a red color, right? Because once you know this, you'll know this. Okay, so please tell me the DF. How many information is needed in this system? If we have an air, liquid, water system, so C will be what? C will be what? 2. 1, 2, 3, 4. Which one? Raise your hand. 1, 2, 3, 4. 1. 0.5. Seems you hate getting scores. You don't like scores. I don't know why. Yes. 2, right? Thank you. Why? Water and air, right? Okay. How many? What's the pi here? 0.5. Yeah, please, let's give the chance to another. Okay, 2, right? Thank you. That's 2, right? Isn't it so easy to get points? No? Or you hate points very much. Okay, you hate scores very much. I don't know why. Anyway, I love it very much. Okay? But anyway, you lose nothing if you get the answer wrong. Right? Okay? So this is 2. That means what? In air, liquid, water system, you need 2 pieces of information in order to complete the system, in order to duplicate the system. So I already gave you the temperature and pressure. So yes, these 2 pieces of information is temperature and pressure in this example. So you can duplicate the system well. Okay? So needed variables temperature and pressure. Okay, Last law. How can you get this? As I just told you, this system is only play with temperature, pressure, molar fraction, and partial pressure of the water, right? So there are 4 things, and you only use 2 equations. Equation 1, Law's law. Equation 2, Dalton's law. That's it. So the first one, Law's law, the things I mark in red color is the things you don't know. So once you have pressure and temperature, as I just told you, if you have temperature, you can get what? Saturated water pressure, water partial pressure in this system by what? Anthony equation, Clausius-Krypton equation, Koch's chart, whatever, right? So you can get this. And then once you get this, you have pressure, you can get what? You can get molar fraction. And once you get molar fraction and the total pressure, you can get what? Partial pressure. Bingo. You get everything. So let me show you how to get this. So T here, so you get this, right? So what you don't know is this one, and you move this P to this place, and then YI will be. First of all, you need to find out. You need to check from table or use Anthony equation or use Clausius-Krypton equation or Koch's chart, right? There are 4 methods. First, table. Find out the table. Second, Clausius-Krypton equation. Third, Anthony equation. Fourth, Koch's chart. Okay? According to this, the textbook in the example 6.3-1 tells us that there's a table in our textbook in table B.3. You can find out this. If the water at 75 Celsius, the saturated vapor pressure will be 289 millimeter mercury. So once you have this, of course, you can get YI, which is YI is what? The total. This is total pressure, right? So 289 divided by 760, that will be 0.38. Okay, 38% of the water in the gas phase. There are 62% of the air in the gas phase. Okay, once you get YI, so this mark this as a from red color to green, to blue. So you solve this problem. And so the dry air is this. How about the partial pressure? Partial pressure P will be this Dalton's law, right? YI times total pressure. So this one, partial pressure, you can get a partial pressure here. So I want you to go home and practice this by yourself. So the key is how to get this. How to get saturated vapor pressure at 75 Celsius for water. Point 1. Point 2 is, do you remember how to use Law's law? So next page is the one, table B.3, vapor pressure of water. And so as you can see, this is ice, this is liquid water. So this is minus 14.0, 14.0, 14.1, 14.23, okay, until here. So this is 0. And this is the number of the partial pressure in the unit of millimeter mercury. Okay, so this is 7, right? 7.2, 15.98 is like this. Okay, the same. So so how can we find out from the vapor pressure of water at 75 Celsius? So if we go to 70, this is the 25, 49, 50, 60, 70, 80, 85 here. Sorry, 75. So 75 is what? 75 is here. 289.1. This is the answer. This is the things you need to get, the number you can get from the table. Okay? And you put this back to the Law's law. Okay? So this is how we use this. So vapor pressure of 4 liquids. So not only as you know, you can get the answer by, as I just said, there are 4 directions, right? You can get the vapor pressure from table, Clausius-Krypton equation, Anton equation, Koch's chart. Of course, you can get from the figures, right? This is different. This is another one. So, for example, the water is here. You might say, "Wow, Professor, Koch's chart tells us this is a straight line, but this is not a straight line. This is a curve." Remember, Koch's chart is what? It's a log-log plot. This is not a log-log plot. Okay, so that's why it's not a straight line. So 75 here, and you can get the pressure. You might say, "Well, Professor, this is not 289." Different units, okay? Different unit. This is kilopascal. Right, okay, so now next topic is that we want to learn a term called superheated vapor. Superheated vapor. What is superheated vapor? Have you heard in Chinese 过热水蒸气? Have you heard about that? No, it's very good at cooking. You know, when you have a microwave, there's a function of superheated microwave. It shouldn't be microwave, it's a superheated oven. Okay, anyway, and dew point, that's what we're going to learn in the next topic. But before that, let's refresh. Right, so let's start to learn what is superheated vapor and what is dew point. So behavior of the gas liquid system saturation, you already learned this because the system is reached to equilibrium. That means the vaporization rate is equal to condensation rate. So the system won't change with the time. It reached to equilibrium, so it doesn't relate with the time. So this is what we call saturation, or the system reached to equilibrium. So at this moment, if the system doesn't, the parameter of the system doesn't vary with the time, so you can find out, you can realize that there's something you want to know, which is the partial pressure of the I species, right? So a gas in equilibrium with the liquid must be saturated with the volatile components of that liquid. So it's the vaporization rate is equal to the condensation rate. Okay, so it reached to equilibrium, the system reached to the equilibrium, and this is saturated vapor. Okay, so at this time, if you have PI, if you have a temperature, you can realize the PI star here. And you, by the Law's law, you can get PI star, you get PI star, you can get PI. So if PI equal to PI star in a gas mixture, that the vapor is saturated. Okay? So this is PI is reached to PI star function of T. So it doesn't change anymore. So any attempt to increase PI, can you increase the PI? If this PI equal to PI star, which is maximum, right? Can you increase this? So you might say, well, Professor, can I introduce more vapors here into this system? No, because it reached the equilibrium, so it will be condensed, right? Okay, so the vapor won't change. You might say, well, Professor, if I increase the pressure in this case, no. If we increase the pressure or you decrease the temperature, it won't change the system because this reached the equilibrium. So it must instead lead to the condensation. It won't change anything. Okay, because the PI star is the maximum volume. Okay? So there's no way to have a PI larger than the pi star. It's impossible. Okay, it's impossible. Okay, so if you might say, well, Professor, is any cases the pi less than pi star and it reach equilibrium? I mean, the pi is always smaller than pi star, right? And pi, if pi equal to pi star, that means it is the maximum. So if the pi is smaller than pi star and reach to equilibrium, is it possible? I should say it's possible, but there's no two phases at this time. That's why the vapor, what we call, is called superheated vapor. So what is superheated vapor? Let's have a scenario in this case. So we have wave air, temperature, and pressure, and you have water, of course, here. And then in the initial stage, T, the time equal to Ti. Ti stand for initial, okay? Initial. Okay, so it's not saturated. So you start to pour water into this system, and of course water will be vaporized, right? You have a Pi. And Pi is less than the Pi star. The Pi star is a function of temperature, of course. But it hasn't reached to equilibrium because the Pi will keep on increasing, right? Until it reached to equilibrium. That means what? The condition one is that the water reduced. Water reduced. And it won't reduce anymore. So it reached to the equilibrium. That means the Yi is saturated vapor. So the vaporization rate is equal to the condensation rate. Okay, this is condition one. The condition two is, you might say, well, Professor, if I don't have enough water, what happens? Okay, so Pi will be equal to Pi star times capital P equal to Pi equal to Yi times P, capital P equal to Pi star function of T. This is Dalton's law. This is, this is Law's law. This is Dalton's law. Okay? Okay, so in that case, this is condition temperature 1 and pressure 1, right? And then if I change the temperature and pressure to make it become temperature 2 or pressure 2, and I make all the vapor, water vaporized. There's no more liquid water in the system. Of course, you have a Yi here, right? So there's no H2O liquid in this system. So this is the case 2, right? This is condition 2. This is condition 1. This is condition 2. So this Y here will be what we call superheated vapor. So if you want to have only one phase in this system, you need to change the temperature and pressure in order to let it reach to one phase, which is the gas phase. So this is what we call condition 2. Is it possible to make this happen? Yes, if we keep on increasing the temperature. If we keep on increasing the temperature, right? And if you keep on decrease the pressure. Okay, and of course you will find a molar fraction of the water in the gas phase. At this time, the pressure here will be always less than the Pi star function of T, right? Because it never reaches the saturated water, saturated vapor. Why? Because once you have another drop of water, this water will vaporize, right? So the pressure, the Yi will increase, the partial pressure will increase. But it never reached to the Pi star until you add enough water, right? So at least this is an equilibrium. The condition doesn't change with the time. But there's no more two phases, only one phase. Okay, the Pi here is less than Pi star function of T. In this case, we call the vapor, in this case, we call superheated vapor. Superheated vapor. Okay, so behavior of the gas-liquid system in superheated vapor is that a vapor present in the gas is less than its saturated amount. Is referred to as a superheated vapor. Why is less than saturated amount? I just told you that if I add more water here, and this water will be vaporized, so it's always not enough. So that's why it's less than a saturated amount. So this is what we call superheated vapor. So Pi will be less than Pi star function of T. And at this time it's equilibrium. It reached to equilibrium, right? So this is what we call, so if you keep on adding water, eventually the superheated vapor will become saturated vapor. If you keep on adding water at the same condition of pressure and temperature. Right? Okay, so that means if you keep on adding water, you'll become equilibrium. You'll be saturated. That's why superheated vapor can become super saturated vapor. Okay? Right. How do you do that? How do you do this? How do you make the superheated vapor become saturated vapor? Without adding water in, you can decrease the temperature. Imagine it's water, a vapor, right? If you decrease, water will be condensed from vapor to liquid. Or you increase the pressure, right? So if this is a closed system, you cannot add more water in. You can change the temperature and pressure to make it to make the vapor condensed. Temperature and pressure. Okay? So you can decrease the system vapor temperature to achieve the condensation in a system containing a superheated vapor, or you can increase the total pressure. Remember, there is a piston with a piston in a container. Increase the pressure or increase the temperature. Okay? Right. So imagine if we decrease the temperature or increase the pressure, if the start point to have a liquid, that's what we call dew point. Dew point. The first drop of the water, or the first drop of the liquid appear in this system. At that time, we call it dew point. Dew point temperature or dew point pressure. Okay? Okay. So this is behavior of a gas system, dew point. So imagine this is a saturated, this is a superheated vapor system. And I decrease the temperature or increase the pressure to have the first drop of liquid come out. And this is what we call dew point. So if a gas containing a single superheated vapor is cooled at constant pressure, the temperature at which the vapor becomes saturated is referred to as a dew point of the gas. Okay? So decrease the temperature or increase the pressure, superheated vapor, and to become what? To become saturated vapor. Okay? So, and then at this moment, if you just change the temperature without changing the pressure, this is what T dew point here. Because it came on decrease the temperature and the first drop of the water come out. So this is what we call dew point temperature. And of course, dew point temperature, you can get the vapor pressure at this moment. Okay? And you also get the partial pressure in the system. Okay. So the differences between the temperature and the dew point temperature of the gas is called degree of the superheated of the gas. So the temperature here, for example, is 100 Celsius. And you start to decrease the temperature to 75, and you see the water drop here. So 100 decreased to 75 means what? The degree of superheating of the gas will be 25, right? Because 100 divided by 75, 100 minus 75 equal to 25. So it's 25 Celsius. So degree of superheating of the gas is that temperature, original temperature, and when the temperature reached the dew point, you got T2 here. Because it depends on the pressure, right? Depends on the different pressure. So this is the degree of the superheating of the gas. As I just told you, 100 decreased to 75, you got a first drop, and this is dew point, right? So you have the dew point temperature will be 75, and 100 will be this one. So 100 minus 75 equal to what? 25. So 25 is the degree of the superheating of the gas. Right, so this is an example. This is an example which is very important. I want you to work with me. So first one is that the material bends around a condenser. Remember the condenser? Condenser is make the things condense, right? Okay, so this is the air. This condition is air, and you have water here. Temperature is 100 Celsius, pressure is 5,260 millimeter mercury. So the system in wet air is 100 and 5,260 millimeter mercury. And vapor, water vapor in the gas phase is 10%. This is VV. VV is what? Is a molar, is volume fraction, right? Volume fraction. Remember, volume fraction equal to molar fraction because of what? Because PV equal to nRT. PV is a proportion of mole. So molar fraction is equal to what? Volume fraction. So if I say VV 10%, that means molar fraction is 10%. Okay, so XI will be, YI will be what? 0.1. 0.1. So calculate the dew point and the degree of the superheated vapor of the air. So in this case is you have 100 Celsius and 5260 millimeter mercury, and then the YI will be H2O will be 0.1. So is this only air or only gas phase? So you need to know what is the partial pressure here at this moment. Can you tell me what is the partial pressure? Yes. What's partial pressure? Dalton's law, right? P equal to YI, PI equal to YI times capital P. So the partial pressure will be 526. Anyway. So this is P, the partial pressure here, which is 526 torr. Torr is a unit of millimeter mercury. Okay, torr here. So is this saturated, or you still have water here? You need to find out. At this moment, 100 Celsius, 5,260 millimeter mercury. Is this the one? So saturated pressure will be what? 1,000 Celsius. If you check the appendix B3, 1,000. The saturated pressure will be for water will be 760 millimeter mercury. It makes sense, right? Because water boil at 1,000 at 1 atm will be 100. Right? Right? Okay, so 525 is smaller than, so PI will be smaller than PI star. Right? PI will smaller than PI star because 526 will be smaller than 760. So this vapor is superheated. Water is superheated. Okay? Okay, so superheated vapor. In that case, how can you get the dew point? So if the partial if if the partial pressure is 526 millimeter mercury, you get the first drop. That's the dew point. So what you can do is what? If you keep the temperature as a constant, you start to reduce the temperature. Okay? Keep the pressure as a constant, reduce the temperature. And once you reach to 526 millimeter mercury, you'll get the first drop. If you start to decrease the temperature from 100 to a certain point, you will get the first drop of the water. And this is what we call dew point. So what is this one? What's dew point? Find out. How can you find out? You can get from a table, right? Okay, you can get it from a table. So what is the vapor pressure of the water at 526? At that temperature, this is called dew point temperature. Okay? So at this moment, if you have the first drop of the water come out, this is what we call saturated vapor instead of superheated vapor. Because it's reached equilibrium, liquid and gas reach equilibrium. So this is saturated vapor. Okay, so saturated vapor, if you find it 526 millimeter mercury, at what temperature? The temperature will be 90. So 90, if you reduce from the temperature from 1000 to 100 to 90, you'll get a first drop. And 90 will be the dew point temperature. Okay? So degree of the superheated of the air is what? 100 divided by 90 equal to 10. So degree of superheated of the air is 10. Okay? So here is that. How do you find out this one? Next page. So remember this vapor is 526 millimeter mercury. Let's find out where is the 526. 528, 9, 526 somewhere around here, right? 525, 527. So this is close 526. So what is this? What's the temperature? 90. Right? So dew point of the temperature is 90. Okay? So you keep on decrease the temperature, become 90 from 100. You get the first drop of the liquid. And this is dew point. Okay? So, for example, from 1000 and 1 atm, right? Okay. Okay, the question 2. So once you reduce the temperature from 1000 to 90, and if I ask you to keep on reduce the temperature to 80, so what's the final composition of the gas phase? So the case 1 is, the condition 1 is from 100 to 90, right? To 90, you got the first drop. To 90, you got the first drop of the water come out. Okay, and you realize why right? You realize why this is saturated vapor. And now I want you to reduce the temperature from 90 to 80. Can you do that? Of course. 100, 90, 80. And then I want you to find out the composition. What's the Yi here? So not only the first drop of water, but you got a lot of water in liquid phase. Right? Because you reduce from 90 to 80, you have a lot of water. And now I want you to find out what's the molar fraction of the water in gas phase. You might say, well, Professor, what's the molar fraction of water in liquid phase? That's 1, right? Because only one condensable component. Okay, so let's find out so again, if I give the temperature and pressure, and according to given phase rule, two out of three pieces of information, you can get another one. Using what? Using Law's law, right? So important thing is Law's law. You need to find out vapor pressure. The vapor pressure here is partial pressure is 355.1 torr. So if you use the things we learned, the flow chart we learned in chapter 4, what can we write for this? This is a condenser. This is condenser, and the condenser, the condition in the condenser is 80 Celsius and 5,260 millimeter mercury. So you have gas phase, you have liquid phase. You condense something in liquid phase. Okay? So the input will be, for example, 100 mole basis, right? And then you have 10% water volume, because this is more anyway, vapor. And what's DBA? Bone dry air. Bone, B-O-N-D, bone dry air. That means no water anyway. So 90%. And temperature 1,100, and then total pressure. And the output is what? So this have water come out. This is pure water. So N1. So N2 is total amount of in the gas phase. And then you don't know the molar fraction in gas phase, like the molar fraction of water and then molar fraction of bone dry air. Okay, a temperature here is 80, from 100 to 80, right? You keep the temperature, pressure as a constant. So you have 3 unknowns here, and you need to find out these 3. Okay, so can you do this for me? Yes, because you have how many equations you need to get? 3 equations. How many species here? 2 species, air and water. So you already have 2 equations. What's another one? The third one. Third equation is what? Relationship with what? With the Y and the TP. This is what we call Law's law. So number 3 equation is using the Law's law to find out the molar fraction of the water in gas phase. I should say vapor. Okay. Okay, so using this equation to have this is third equation. You might say, well, Professor, I know total pressure, but I don't know the saturated vapor pressure of water. Of course, you know this is temperature here. So again, find out from the text, from the table, Anthony equation, Clausius-Clapeyron equation, whatever, Koch chart. Okay, so let's find out the temperature 80. What is the vapor pressure? 80 here. This is 355.1. Right. Are you with me so far? Or you totally lose? Okay, if you please go home and practice and learn this. If you don't understand, please repeat, because we'll keep on doing this in chapter 6. Okay? Okay, the numbers, so what you can do is this. I just told you. So what you get the answer. So the question 3 is, instead of increase the temperature, instead of tuning the temperature, I change the pressure from 5,260 to become 8,500 millimeter mercury. So what happened? If we increase the pressure, that means what? It will be condensed, right? The vapor will be condensed, become liquid water. Okay? So you will have water. Again, you can find out the molar fraction at this moment. Molar fraction of water, vapor at this moment. Why? Because you use Law's law. Okay, so again, this is the flow chart. So from saturated heated to, for the first drop, which is 7,600 millimeter mercury, this is the dew point pressure. And you increase the pressure to be condensed. Okay, this is the same way to decrease the temperature. This is increase the pressure. And you please go home and do the practice by yourself. Okay. So I just let you know how to do it. So I don't want to waste your time. So please practice this by yourself. So question 4 is that the question 4 is that what's going wrong? What's going on if it's something wrong? But anyway, this is the things. So this is superheated vapor steam. So why we need to know? We need to learn superheated vapor because this is power station. The important thing in the power station is turbine generator, right? Turbine generator is very important. And what kind of energy can push the power push the turbine? Okay, I hope you remember this power station. We use chemical energy to become thermal energy. From thermal energy become mechanical energy. From mechanical energy to become electrical energy. So that's why you get electricity. You can use the lamp, you can use the computer, you can use any electricity products at home, right? So the core of this power station is turbine. How do you drive the turbine? How do you move the turbine to make it to have the mechanical energy? Using superheated vapor. You don't allow any liquid water in this system, no. And superheated vapor has a tremendous energy, so this energy can push the turbine to move from the heat energy to become thermal energy. So from thermal energy to become mechanical energy, and from mechanical energy to become electricity. Okay, so this is what you need to know. So you need to know what kind of condition can make superheated vapor, and what temperature and what pressure. Okay, instead of using water, you probably use another gas or liquid, right? So this is the example. And of course, okay. Right, so I think I better stop here now. Right, I think we had enough today. So I want